Electron configurations. This is a background information about the significance of electron configurations, but it's also necessary to understand this before you can go ahead and write electron configurations. Electron configurations is nothing more than describing where electrons live, and our goal will be to write something similar to what appears on your screen. Let's look at what those numbers and letters mean. The red numbers are representative of the principal quantum energy levels, which is represented by the letter N. This describes how far the electrons are from the nucleus. They'll always be whole numbers, meaning 1, 2, 3. They'll never be a decimal point or a fraction. But as the principal quantum energy level increases, it's telling us that the atom is getting larger. And if the atom is getting larger, then the electrons are getting further away from the positive nucleus. Haven't you ever wondered on a Saturday night why those negative electrons don't immediately get attracted to that positive nucleus? Because positives and negatives attract each other, and they do. It's called nuclear attraction. So there is that attraction between the electrons and the positive nucleus. But as the atom gets bigger, as the quantum energy levels increase, those electrons get further and further away from the influence of that positive nucleus. It's important knowing that. It helps explain the periodic trends, which we'll just talk about later in this chapter. Let's look at the letters up there. These are representative of the shapes of where the electrons reside. Now, quantum energy levels is based on quantum physics, very complex math, which we will not discuss here, but they've made it a little bit simple by helping us understand what these complex numbers mean. So the shapes are grounded in a 3D representation on an XYZ axis. And so it's almost as if you took your camera and you opened the shutter and you took a picture of those zooming electrons. What shape would that look like after 24 hours? So we have an S-shaped sublevel, which are circular. Again, think about a ball, because you need to think in 3D terms. And so all S-shaped sublevels are balls, and each of those can hold a maximum of 2 electrons. If you look over here on the right, you can see that all of these are S orbitals. The only thing that's different is that the quantum energy levels are different. Again, remember the rules. As you increase the quantum energy levels, you're increasing the size of the atom, increasing the distance the electrons are from that nucleus. So it makes sense that the 3s orbital, which is a ball, would be a larger ball than a 1s orbital. P-shaped sublevels are pear-shaped. They have this shape right here. And because it's based on math, they live on the XYZ axes. And if you took all 3 of them and put them and overlapped them here, it would look like this. I want you to remember that there are 3 p sublevels. Each of these shapes up here can hold a maximum of 2 electrons. So all p-shaped sublevels can hold 6 electrons. D, dumbbell-shaped sublevels, have funny shapes that look like this, but there are 5 of them, and each of those D-shaped sublevels can hold a maximum of 2 electrons. So the D-shaped sublevels, all of them together, can hold a maximum of 10. Well, when you get to the F-shaped sublevels, let's just say they're pretty complex. They can't even come up with a shape that describes them. But one thing they do have is 7 Fs. Each of those hold 2 electrons for a total of 14 electrons. Here's a chart summarizing this. They'll talk about how many sublevels you have of each of these and what are the maximum number of electrons that each of those shaped sublevels can have. And as we said before, there are 3 p's on the XYZ axes, and the maximum number of electrons they can hold are 6. So every time you write an electron configuration, every sublevel has a quantum number in front of it. So this is the 4th energy level, p-shaped sublevel. The superscript represents how many electrons are in there. So in the 4th energy level, p-shaped sublevel, there are 5 electrons in there. Here's a representation of all the quantum energy levels here and describing what kind of shapes exist in each of these. At n equals 1, which is the closest to the green nucleus in this example, it's the smallest shape, so smallest area I should say, and so the only shape that can reside in there is the S-shaped sublevel. At n equals 2, you're getting further away from the nucleus, you're getting larger, and so you can fit S and P-shaped sublevels. Again, we're at n equals 3, it's larger, you can have SPs, and this is where the Ds first appear. Fourth energy level, furthest away from the nucleus in this example, can hold the most shapes, S, P, D, and F. It makes sense, larger area can hold more things. This chart can be similarly found in your lecture notes. It's an important chart to understand what it's telling you. It's everything that's in this atom written in a chart format. These are your principal quantum energy numbers. These are the shapes allowed in each of those energy levels. These represent the maximum number of electrons that can be held in each of those sublevels. It follows again that S's hold 2, P's hold 6, D's hold 10. So in the third energy level, you can hold a maximum of 18 electrons. The fourth energy level, when you add all of those up, can hold a maximum of 32 electrons.